In this video, we're going to learn a way to look at an ionic equation of a particular reaction to evaluate exactly what's going on. Because we're going to see in many of these double displacement, or as we'll see later, single replacement reactions, we will have components that don't actually do anything in the reaction. They're just hanging around unchanged from start to finish. And sometimes it's helpful to remove those, just to make it very clear what's actually happening, what chemistry is happening. With an ionic equation, we're used to seeing equations like this. These are called molecular equations. Where we have our compounds in the reactants turning into our products and all of their states of matter. However, this is kind of useful, but it doesn't really describe reality as much. We're going to see components of this do not necessarily need to be there. We could replace them with other things and still get the same reaction to happen. And in order to do that, we have to evaluate what's changed over the course of the reaction and what stays the same. And so what we want to do is look at all of the ions present in the reactants and the products. So let's look at all the ions. And this is going to be what's called a complete ionic equation. And for this, what we're going to do is anything that is aqueous, we are going to split apart into its ions. We're going to write out all the ions here. So, if we do this, our first compound is the sodium bicarbonate. We'll have the sodium ion, the bicarbonate ion. We have the acetic acid, which we can break apart as well. Great. In our products, we have water. That's not aqueous, so we leave that alone. We have CO2 that is also not aqueous, so leave that alone. And then we have the aqueous sodium acetate. So we've got the sodium ion there plus the acetate ion. So we have all of our ions out here. So this is the complete ionic equation. We're able to see everything that's in this reaction at the beginning and everything that's present in the solution at the end. And so when we take a look here, we might see some ions are unchanged. In this case, we have sodium ion on both sides of this equation. We see that it is unchanged. It is exactly the same as it is on the product side. Sodium plus aqueous. On the reactants, sodium plus aqueous on the products. They are identical. And we also see that the acetate ion is also unchanged. C2H3O2 minus aqueous on both sides. They're exactly equal to each other. We call these spectator ions. They are spectators because they don't do anything. We could replace these with other ions, and we would generally not see anything else happen. Meaning the same reaction would take place if we used potassium instead, or nitrate instead of acetate, or chloride even. So we have spectator ions don't matter necessarily. They're there for charge balancing purposes, but that's all they do. So we could replace them if we want, and the reaction would still happen exactly the same way as it did before. If we remove the spectators, because if we had an algebraic equation, x plus 5 equals y plus 5, we could subtract 5 from both sides, right? And we'd get x equals y, right? Subtract 5 from both sides. We can do the same thing with chemical equations. If we have sodium ion on both sides, we can remove it. Subtract a sodium from each side. All right, let's get rid of this algebra. We don't need to do too much math yet in this chapter. So if we remove the spectators, We're going to write everything else that's not exactly identical, and CO2 gas. And this is what's called the net ionic equation. It tells us exactly what is happening in this reaction. Bicarbonate and hydrogen ions are coming together to form water and CO2. That's the chemistry that's happening here. The sodium and acetate don't matter. They're just there for charge balancing. Like I said, we could replace those. We could say potassium bicarbonate instead. No problem. It would work exactly the same way. Instead of acetic acid, we use hydrochloric acid or sulfuric acid. Doesn't matter. In either case, we're going to have the spectator ions not being present. We will see, by the way, our common spectator ions are, see if we can guess it, if we go up all the way to our solubility rules, all these things in blue are very often spectators. So sodium, lithium, potassium, rubidium, ammonium, acetate, and nitrate are always spectators. Ammonium, we'll worry about that later because that one can do some weird stuff, but the rest of them are always spectators, no exceptions. So we can interchange them. Switch out for your sodium for lithium or potassium or rubidium, no problem. Your reaction will work exactly the same way. Your halides are generally going to be spectators as well, unless they're part of some precipitate. And sulfate, the same way, will generally be a spectator ion unless it's forming some precipitate. All right, so the red ones would be exceptions, remember. So everything else in blue here generally should be a spectator. So that's the hint for you. So let's take a look. Indeed, we have sodium and acetate here. Those are in our blue list up above. For solubility, those will be spectators. All right, so we can see exactly what's happening here. If we take a look at another one, we saw that we had the silver nitrate and the calcium bromide forming silver bromide and calcium nitrate. These were aqueous, aqueous, solid, aqueous. We can determine its ionic equations as well. So this is a new reaction. If we want to do the complete ionic equation, we break apart everything that's aqueous into the ions that make it up. Technically speaking, we should balance this, so you should get the following when you balance it. So we have 2 silver ions plus 2 nitrate ions plus a calcium ion plus 2 bromide ions. Right? I'm going to write our product side on the bottom here because I don't have room. We'll have our 2 silver bromide solid. Do not split that one up if it's solid. And then we have the calcium ion plus the 2 nitrate ions. So we want to look what's exactly the same on both sides. Is 2 silver plus aqueous the same on both sides? It is not. We do not have 2 Ag plus Aq on both sides. Do we have 2 nitrate aqueous on both sides? Indeed we do. These two are the same. And remember, nitrate should always be a spectator for this type of reaction. Let's check our next one. Calcium 2 plus aqueous. Yes, indeed, we do have that on both sides. And then 2 bromide ions. We do not have 2 bromide ions on the right side, or rather the product side. So we have circled our spectators. The calcium and the nitrate are spectators here. So overall what's happening here is silver ions and bromide ions are combining to make silver bromide. And indeed we have double, the equation all has 2's everywhere. That's just because of the counter ions involved here. Our net ionic equation we could keep as this, but generally speaking we'll reduce it. So we'll have silver plus bromide turns into silver bromide, solid. So this is the net ionic equation. This again tells us we can put other counter ions in here that could work as well. We could say silver acetate plus sodium bromide would give us the same products. We would still see the same net ionic equation. All right, the last thing about this, if your net ionic equation doesn't exist, meaning everything's a spectator ion, is nothing. If you have no net ionic equation, that tells us no reaction took place. And I'll give you an example of that right now. If you have, say, calcium nitrate plus HCl, I'll let you do this one. You should see that once you produce the products here, no reaction will take place. Switch everything around, you get nitric acid and calcium chloride. Everything is aqueous, so everything's going to break apart. So no reaction took place here. All right, so that is our double displacement. In our next one, we're going to take a look at electron transfer processes. So with acid-base, we look at proton transfers, right? We have hydrogen ions moving from substance to substance. In our next one, we'll look at electrons moving around.